This exercise related to gravitational field strength and the Newton's law of gravitation. Um, as you can see here, in this question, electrostatic forces and the gravitational forces can both be modeled by the idea of the field, give one similarity and one difference between the electric and the gravitational field. We have just discussed now in the session that what are the similarities between these forces, how the forces are similar. They have infinite range. You can also say and follow the inverse square law. Anyone, or you can say the difference is like the gravitational field is a force experienced by the mass, where the electric field is a force experienced by the charge. Gravitational is always attractive, but the electric is attractive or repulsive. You can also say that. Question 7. The graph shows how the gravitational field strength G of Earth vary with the distance r. It follows the inverse square relation. The r is given in a multiples of radius of Earth, like it's means actually it's like a comparison is there when the ratio r to re is 1. It means the radius of the Earth, like object, is on the surface. So this distance is a radius of Earth, and the value is given r over re is 1. What when r over re is 1? So r is equals to re. It means the object is on the surface. When object is on the surface, the strength of a gravity is 9.8 Newton per kilogram or meter per second square if we represent acceleration due to gravity. Show that G obeys the inverse square. What is the meaning of inverse square? Like if you double the distance, what will happen to the force? Force will decrease by 4. When we take this value, it's 9.8. When we double the distance, this is 2.4. So what happened to the value of the F? If this were like the value of a G, I mean, so that this is G now and this is G. So if 9.8 is divided by, because if a distance is double, here it was 1 and now 2. So means what happened to a distance? It is double. But what happened to the force? It will decrease and it will decrease by 4. 9.8 divided by 4. So what we'll get? We'll get 2.4. So we just have to show that it's obeying the inverse square relation. Is it clear, this one? Just use any two values. The next we have the satellite is launched from the surface of the Earth into the orbit, which is 5 times RE above the surface. The change in gravitational potential energy of a mass m when it experiences a vertical displacement. State why this expression cannot be used to calculate the change in gravitational potential energy. Like if I lift any object above the Earth's surface, I can use the formula that gravitational potential energy is mgh. But when an object is moving away from the Earth's surface, I cannot use this formula. So main reason is that that's good, Hashim, that the gravity is not constant because the gravity is changing. Here, when we talk about the reference with related to the Earth's surface, the value of the G at this point was 9.8 and value of a G is also 9.8. So it's same when it is moving, but when we compare the movement reference to the Earth, the gravity is not constant. Like gravity here is 9.8, but the gravity here is not 9.8. It is less than 9.8. Calculate the change in a gravitational potential energy for the satellites. So how you work out the change in the gravitational potential energy for especially for the satellites? You just take a difference of the value of a g, the potential. For satellites, the potential at a certain point is given by a formula. Like potential at a certain point is given by a formula Gm over R. So what we will do? We need the change in gravitational potential energy. This is how we got the potential, and then if we need a potential energy, we just multiply by the mass. So what we will do? We'll find, or you need a potential this is a potential. If you need a potential energy, you'll multiply by mass as well, because this is a formula to get the potential of the planets. It can also be represented by phi. So phi is equals to Gm over R, which is the potential at a certain point for the planets. G is not included because it is not constant here. So what we will do, we'll find the potential at this point, which is on the Earth surface. Then we'll find the potential, the satellite, because the radius of Earth given mass of a satellite is there, and it is 5 RE, like the total distance. So we'll find the potential at this point, and we take a difference of the two potential, phi 1 and phi 2. So we'll just take a difference of the two potential to know the change in the potential. And the change in the potential multiplied by mass, so it will give us? It will give us the gravitational potential energy. Phi is actually, it's, yes, it is. Radius is always taken from the center, and phi is actually it's the potential. It's not the gravitational potential. It's the potential at a certain point in the space where the so when we don't have a constant gravity, we use the potential equals to Gm over R, or gravitational potential, and just at the last multiply by mass. So if we have a planet